Have you ever wondered how the first machines learned to turn fire, steam, pressure, and fuel into controlled motion? Before electronics, sensors, and automatic systems, every revolution depended on valves, pistons, flywheels, gears, cables, and human judgment. From atmospheric engines and giant steam machines to early automobiles and locomotives, this journey reveals how engineers transformed raw energy into mechanical power that could move the world. The story begins with one of the strangest early internal combustion machines ever built, the Otto-Langen atmospheric engine. At the Rough and Tumble gathering in Kansas, Pennsylvania, Wayne Grenning prepares a reproduction of the 1867 design, rated at only half a horsepower. Starting it is a completely manual ritual. The ignition must be prepared, the air and fuel valves adjusted by hand, and the flywheel turned until the piston begins its working cycle. Nothing is hidden behind electronics or automatic controls. Every movement exposes the basic problem early engine builders were trying to solve: how to turn a brief combustion event into useful mechanical work. Inside the vertical cylinder, a combustible mixture is ignited and drives the free piston upward. Unlike later engines, the expanding gases do not deliver the main power stroke through a conventional crankshaft. Instead, after the piston rises, atmospheric pressure and gravity help pull it back downward. That descending motion is transferred through the engine's mechanism, producing useful rotation at the output. The demonstration then moves to an original Otto-Langen engine from 1869, also rated at half a horsepower, followed by a larger 1873 3-horsepower machine built by Crossley Brothers and loaned from the Henry Ford Museum. Seen operating together, the machines reveal how carefully early engineers controlled combustion, valve timing, piston movement, and flywheel momentum, long before modern engine management existed. The demonstration then moves to an original Otto-Langen engine from 1869, also rated at half a horsepower, followed by a larger 1873 3-horsepower machine built by Crossley Brothers and loaned from the Henry Ford Museum. Seen operating together, the machines reveal how carefully early engineers controlled combustion, valve timing, piston movement, and flywheel momentum, long before modern engine management existed. Bridge. From experimental combustion, the next machine shows how slow power became dependable. From atmospheric combustion, the story jumps forward to a machine built for steady work, the 1931 Ruston 5HR. This green stationary oil engine produces 22 brake horsepower at just 320 revolutions per minute. Designed as a cold start oil engine, it turns its large flywheel with a slow, even rhythm. The close-up footage emphasizes what mattered in machines like this: low-speed torque, mechanical simplicity, durability, and reliable continuous operation under load. Bridge. Once power could run steadily, engineers began carrying that force across the ground. But mechanical power was not confined to stationary engines. Big Ben, an Aveling and Porter Class A8 steam traction engine built in 1894, shows how steam power could move heavy machinery across farms and estates. Built in Rochester, Kent, this 8-horsepower compound engine was designed for demanding agricultural work. Its working life began on large estates before preservation brought it into living history collections. In operation, the machine combines boiler, cylinders, gearing, wheels, and controls into one mobile power unit. Steam pressure becomes piston motion becomes rotation, and rotation finally becomes traction at the ground for sustained heavy work. Bridge. Mobile steam solved movement, but pumping demanded something larger, slower, and steadier. Steam could also remain fixed in one place and perform enormous work for decades. At Strumpshaw Steam Museum, a Glenfield beam pumping engine from 1893 demonstrates that role. Originally one of two machines installed at Addington Pumping Station in Croydon, it was built by Glenfield and Company of Kilmarnock. The engine develops about 125 horsepower while turning at only 14 to 16 revolutions per minute, using steam supplied at roughly 100 pounds per square inch from hand-fired Cornish boilers. Its operation is slow enough for every mechanical relationship to be seen. Steam enters the cylinders and expands through a Wolff compound arrangement, allowing the energy in the steam to be used in stages rather than exhausted after a single expansion. The reciprocating movement is transferred through the large A-frame beam and connecting mechanism. From there, the crank converts the back and forth motion into rotation, while the massive cast flywheel stores momentum and smooths the cycle. The camera moves around the engine instead of hiding its complexity. The flywheel turns steadily. Cranks and rods rise and fall. Valves admit and release steam. The mechanical governor responds to speed, helping regulate the engine without electronic sensors. Polished metal joints, painted castings, and exposed linkages make the control system visible as a physical sequence of forces. What looks graceful is actually a carefully balanced machine. Steam pressure pushes, the compound cylinders extract energy, the beam transfers force, the crank changes direction, and the flywheel carries the mechanism through each dead point. At only a few revolutions every several seconds, the entire thermodynamic process becomes readable to the eye. This is not speed for its own sake. It is controlled, continuous power engineered for pumping, where reliability and smooth operation mattered more than rapid rotation, with every stroke repeating predictably through long working hours. Bridge. From pumping water, steam power moved back outdoors to reshape entire fields. The next machine takes steam power back into the field, but its job is more specialised than simple traction. Fowler BB1 number 15451, known as Victory, represents a system built for cable ploughing. Rather than driving across the field while dragging a plough behind it, a Fowler ploughing engine works from the edge. Two engines are positioned on opposite sides of the field, and each carries a large winding drum beneath the boiler. A steel cable runs from one engine toward a balance plough working between them. One machine winds in its cable and pulls the plough across the soil while the engine on the opposite side pays out. When the plough reaches the end of the pass, the system is reset and the pull reverses. The second engine then becomes the pulling machine. By alternating in this way, the pair can move a heavy plough back and forth without forcing either steam engine to cross soft cultivated ground. Inside Victory, steam is used through a compound engine, typically associated with high-powered agricultural machines of this class. Steam expands in stages across two cylinders, extracting more useful work before exhaust and improving fuel economy. That power turns the gearing and, crucially, the cable drum hidden below the chassis. For the operator, the machine is a coordination problem. Boiler pressure must be maintained, steam admission controlled, drum speed managed, and cable tension watched continuously. Too little pull wastes time. Too much or badly timed tension can shock the equipment. The two engines must work as a matched system across the width of the field. Seen up close, Victory is therefore more than a self-propelled steam vehicle. Its wheels move the engine into position, but the real working force travels through a long steel cable. Steam becomes piston movement, gearing becomes drum rotation, and drum rotation becomes a controlled horizontal pull stretching across the landscape, turning stationary power into mobile fieldwork. Bridge. To understand that system completely, we now watch the Fowler work under load. The same Fowler double B1 becomes even easier to understand when the camera follows it during actual ploughing at Little Casterton. Built in 1925, the engine remains near the field boundary while the cable system does the travelling. Beneath the machine, the winding drum reels in the steel cable. Across the field, that cable is attached to a balance plough designed to work in either direction. As the drum turns, the cable tightens and the plough begins moving through the soil. A person rides on the plough, steering it and adjusting the working depth so the blades stay aligned with the intended furrow. The engine itself does not chase the implement. It supplies the pulling force from a fixed position, allowing a very heavy tool to cross ground that would be difficult for a large steam machine to traverse repeatedly. When the plough approaches the engine at the end of a pass, the operation changes. Workers move towards the implement, check its position, and prepare it for the next pull. The balance plough is turned or reversed, so the opposite set of blades can work. Then the engine at the far side of the field takes over, winding in its own cable and drawing the plough back in the opposite direction. The cycle depends on timing between people, machinery, and two distant power units. One side pulls while the other releases. The plougher cuts, arrives, is reset, and returns. Each pass advances cultivation across the field without requiring the steam engines themselves to travel with the implement. This footage reveals why cable ploughing was an engineered system rather than a single machine. The boiler provides steam, the engine produces rotation, the drum creates cable tension, and the cable transfers that power hundreds of feet to the working tool with precision. Bridge. Then combustion returned, not to a field machine, but to personal transportation. After steam power learned to move implements from a distance, early automobile builders faced a different challenge: making a compact engine move an entire vehicle directly. The 1896 Ford Quadricycle shows that transition in its simplest form. This reproduction places a two-cylinder gasoline engine at the rear, where its exposed mechanism makes the starting and driving sequence easy to follow. There is no electric starter. The engine is brought to life by turning the flywheel manually. Once combustion begins, the cylinders fire with the sharp, uneven sound typical of early internal combustion machines. Fuel and ignition create repeated pressure pulses, but keeping the engine running is only the first step. That rotation must then reach the road wheels. Power leaves the engine through a belt drive arrangement and continues through chain transmission to the rear wheels. The layout is light and mechanically direct, with little separation between the power source and the vehicle structure. Small glass lubricators feed oil by drip into the cylinders, making lubrication another visible task, rather than a sealed automatic system. Brass pipes and exposed valves show how fuel, air, ignition, and oil were managed with basic hardware. The driver sits on the simple seat and steers with a tiller connected to the front wheel. Those wheels are narrow and spoked, resembling oversized bicycle wheels more than the wheels of a later automobile. With the engine running and the transmission engaged, the quadricycle moves onto the street, turns corners, and travels at a moderate pace. What matters is not its speed. The important achievement is integration. A compact gasoline engine, lubrication system, belt, chains, steering control, frame, and four wheels now work as one machine. Unlike the Fowler system, power no longer crosses a field through a cable. Unlike the beam engine, it is not anchored to a foundation. The engine travels with the load it drives. That change transforms the relationship between machine and operator. Starting, steering, lubrication, and power delivery are all concentrated around one lightweight vehicle. The driver is no longer supervising a remote working mechanism. He is carrying the engine with him. In the quadricycle, early internal combustion becomes personal transportation, and a basic mechanical problem shifts from producing motion to controlling where that motion goes. Every turn of the flywheel, every drip of oil, and every movement of the tiller exposes a vehicle still close to its experimental mechanical roots for everyone watching. Bridge. Ford was not alone. Another early design reveals the four-stroke path clearly. A year earlier in the story of the automobile, Benz had already demonstrated another route toward practical internal combustion. Here, a one-third scale working model reproduces the 1887 Benz engine used in the patent motorwagon era. On the test bench, the engine runs with a large horizontal flywheel that stores rotational momentum between firing events. Ignition is switched on, producing timed sparks as the mechanism turns. The visible cycle reveals the essentials of a four-stroke gasoline engine. The cylinder draws in the air-fuel mixture, the piston compresses it, combustion drives the working stroke, and the exhaust valve releases spent gases.
Compared with the Otto-Langen, the concept is more compact and cyclic,
with piston motion organized around continuous crankshaft rotation each revolution. Bridge. Yet decades earlier, steam had already attempted something even more ambitious: road travel. Long before gasoline engines became compact enough for road vehicles, Richard Trevithick had attacked the mobility problem with high-pressure steam. The puffing devil, reproduction, operated during Trevithick Day in Camborne, recreates the road locomotive first demonstrated in 1801. Instead of hiding the machinery, the vehicle carries its boiler, controls, fire, and working mechanism openly through the street. Starting and maintaining such a machine is a continuous manual process. Operators manage the steam valves directly, monitor the engine's behavior, and feed coal into the fire to keep heat entering the boiler. Water is converted into pressurized steam. That steam is admitted to the working mechanism, the resulting piston movement is transmitted to the drive system, and the machine advances under its own power. Every stage depends on human attention because fuel supply, pressure, and steam admission must remain coordinated. As the puffing devil moves through Bassett Street, the scale of the experiment becomes clear. This is not a stationary engine transmitting power to a pump or winding drum. The entire steam plant is moving with its own weight, carrying the energy source, boiler, mechanism, operators, and controls together. The road beneath it becomes part of the engineering challenge. The footage also shows technicians in period clothing working around the machine while crowds line the street. Their presence emphasizes how exposed early powered transport was. Heat, steam, fire, moving parts, and manual controls all occupied the same working space. Trevithick's achievement was therefore not simply making a steam engine run. The important step was making a sufficiently powerful steam system carry itself. The puffing devil demonstrates the logic that would soon become central to locomotion: generate pressure on board, convert it into repeated mechanical motion, transmit that motion to the wheels, and control the machine while it is moving. From here, the next destination was obvious: the railway, where guided steel wheels could turn steam power into a more controlled form of transport forward. Bridge. Once steam could carry itself on roads, rails offered a more controlled route. The final machine brings the story to a mature form of exposed internal combustion engineering. The Merrick Eclipse sideshaft hit-and-miss engine, rated at 15 horsepower and turning at about 240 revolutions per minute, it is slow enough for the eye to follow, yet powerful enough to make every moving component feel substantial. Its 54-inch flywheels dominate the rhythm of the machine, while the sideshaft, governor, valves, crank, and ignition system reveal how speed is controlled without electronics.
Another view of the governor. Give you a general overview of the engine here.
The defining feature is the sideshaft. Instead of concentrating every timing function inside a closed engine block, a shaft runs along the side of the machine and mechanically coordinates the inlet and exhaust valves. As the engine rotates, this shaft translates crankshaft motion into precisely timed valve actions. The sequence is visible. Rotation drives the timing mechanism. The polder mechanism operates the valves, and the valves control when fresh charge enters and when exhaust gases leave.
The exhaust pipe is 2.5 inches. And there's a 1-inch port pipe has ported exhaust.
Speed regulation comes from a flyball governor working with the hit-and-miss principle. As engine speed changes, the governor responds mechanically and influences the intake operation. When power is needed, the engine allows a firing cycle, a hit. When the flywheels are already carrying enough momentum and the target speed has been reached, the governing system can prevent another powered cycle, a miss. The engine then coasts on stored flywheel energy until speed falls enough for combustion to resume. That behavior gives the machine its unmistakable rhythm. A combustion event accelerates the rotating assembly. The heavy flywheels store that energy. Several revolutions may then pass with the engine coasting, depending on the governor's demand. When speed drops, the mechanism again permits the conditions needed for another firing event. Instead of continuously adding power every possible cycle, the engine adds power only when mechanical speed control calls for it. The Myrick Eclipse uses hot tube ignition. Rather than relying on modern electronic systems, the engine uses a heated tube as the ignition source for the combustible charge. Combined with the exposed valve gear and governor, it creates a machine in which combustion timing, airflow, exhaust, and speed regulation can all be understood by watching parts move. The engine carries 54-inch diameter flywheels with faces 5.5 inches wide, and its exhaust system includes a 2.5-inch pipe with an auxiliary exhaust port. A disc crank forms part of the rotating mechanism, while the intake passage leads directly into the engine base. Viewed after every machine before it, the Myrick Eclipse feels like a summary of more than a century of mechanical problem solving. The Otto-Langen showed how combustion and atmospheric pressure could create useful motion. Steam engines demonstrated how pressure could be expanded, transferred, geared, and applied to pumps, fields, roads, and rails. Early automobiles packaged combustion, transmission, lubrication, and steering into mobile machines. Here, the hit-and-miss engine brings those same questions back into one exposed stationary mechanism. How should fuel enter? When should gases leave? How should ignition occur? How can speed remain stable as load changes? The Myrick answers each question with visible hardware: side shaft, valves, hot tube, governor, crank, and flywheels. There is no hidden computer deciding what happens next. The engine measures its own speed mechanically, stores energy physically, and fires only when its governing system demands more power. That is what connects every machine in this journey. Their fuels, layouts, and purposes differ, but each one solves the same fundamental problem. Transform energy into controlled motion, then keep that motion useful, repeatable, and manageable. From atmospheric pistons to steam beams, cable drums, road vehicles, locomotives, and hit-and-miss governors, the history of machinery is clearly visible in the movement of the parts themselves.